Hello. Welcome to an adventure. I hope that you're all having a good week. I also hope that you can see and hear me. Let's see. Hello, NeoGets. Hi, Matt M33. Hi, Stephen Joyce. It's good to see you. Somehow it's Wednesday. Somehow it's February. Hi, Key Squared. Yeah. Somehow a February in Wednesday, a Wednesday in February happened. And it has been really rather snowy here. We had snow and ice, and then a week later we got more snow on that, and today we're getting some rain and snow. So it's fine, except that what we've had, they generally are not prepared to deal with here, so travel has been a little interesting, but that's okay. Also, one announcement for just the stream in general. The VODs were going up on the library's YouTube, and you may have noticed that last week's isn't there yet. That's because I am in the process of creating a YouTube channel specifically for special collections, which right now will just be Archival Adventures. The channel exists, but I haven't actually got anything on there yet. And so I was holding off putting last week's VOD up so that I can put it on the new channel. Hopefully I will have time to work on that tomorrow. But the playlists that were in some of the commands probably are not functional anymore, because there were changes that had to happen on the library's YouTube. And so Archival Adventures there, where it used to be divided into multiple playlists, is collapsed down into just one playlist now. All of the content that was there is still there, and you should be able to find it if you're looking for it. And the videos themselves, if we had direct links to the videos, those should work. But yeah, a couple changes. I decided to go with a departmental YouTube rather than just a YouTube for the show. In case we decide we want to put some other stuff on YouTube, there's a place to do it. So, yeah. Anyway, how is everybody? I hope you're doing well. Today, we will be traveling through the archives on yet another stream of material from the Archives of American Aerospace Exploration. It's AAAE, and I always stumble over what it is. But let's go ahead and look at the finding aid, which may look slightly different to you than what I usually share as the finding aid. And that's because the usual site, which is hosted and administered at the University of Virginia, they're making some changes, and it is currently not loading for me. So this is the public side of the system that we use to actually create the finding aids. But today we're going to look at the John D. Clark papers. And so the organization of the finding aid is slightly different. It includes personal and professional papers of chemist and science fiction writer John D. Clark, dating from 1923 to 1988. Yes, chemist and sci-fi writer. This week we will not be looking at the sci-fi writer stuff. That is planned for a follow-up episode of John D. Clark Papers. Today, we're exploring the care and feeding of rockets. I should check the finding aid command. Yeah, that bitly's not going to take you... Well, it will, but it won't take you to the right place. It goes to the finding aid, just not the one that's going to load. That's okay. Let me grab the one that will load and update that real quick. But yeah, give me 1 second, because updating this and talking at the same time, slightly difficult. Oh dear. Well, Moobot doesn't want to load either. What is going on with the interwebs? I will attempt to update that command at some point. Anyway, let's... Oh, there we go. Okay, hopefully it will work now. Let's try. Yep, okay. So that should point you to what's on the screen. Okay, so who is this John Clark person? Other than being a chemist and a sci-fi author. John Drury Clark. Let's see if I can make this bigger and actually have it be bigger? Okay. John Drury Clark, born August 15th, 1907 in Fairbanks, Alaska. Graduated from Fairbanks High School in 1925, went to the University of Alaska and the California Institute of Technology. Hi, Shadows. Got a bachelor's in physical chemistry and then a Master of Science degree from the University of Wisconsin and a PhD from Stanford. Interesting how it shows... Whatever. In the early 30s, he worked at General Electric, but by 1949, he was with the Naval Air Rocket Program, and he worked there until he retired in 1970. He was the chief chemist at the Naval Air Rocket Test Station and its successor department. He worked in the Liquid Propulsion Laboratory at the Picatinny Arsenal in Dover, New Jersey. Under Clark's direction, a new family of storable, high-energy liquid propellants, later used in the Apollo program, was developed by Navy civilian scientists in 1959. So, the care and feeding of rockets that we will explore, and that is a phrase that I got from the collection, is all about the development of the first liquid rocket fuels here in the US. So that is the plan. Ooh, Shadows, thank you so much for the 10 stream streak. Okay. There is, of course, in this finding aid, a list of the contents, which has many, many things. I'm going to make it a little bit smaller. So there's a lot of this general correspondence, and then you get into correspondence with Isaac Asimov, correspondence with Ben Bova, correspondence with John Campbell. Like, we'll look at that next time when we're talking his sci-fi stuff. So most of our stuff is going to be from like the reports and research materials and stuff like that today, because we're focused on the rocketry stuff. Anywho, let's explore. What is showing up? Ah! I was like, there's something in the field of view that isn't supposed to be there. Okay. I have glanced while I was looking for an image. Beyond that, I don't really know. The first folder I have for you. Yeah, it is physics. Physicsy. Hi, Sayuri. I keep forgetting how things work. I'm not just today. Hang on one second. I'm grabbing a supplemental light here. All right. I want to zoom in. Thank you. Autofocus. And do this. Okay. Nart's LRPL period photographs. Nart's. That would be the Naval Air Rocket Testing Station, I think is what it was. A menace to the archive's shadows. So we'll start with some photos. This one is the one that I used as the image for the the cover image for today's stream. It's an image of Clark. I was looking for an image of a rocket, but I couldn't find one. So in the collection. So we got one of him like posing with all this chemistry equipment. Ooh, congratulations, NeoGets. You've been randomly selected as VIP for the stream. Enjoy your digital gemstone and the ability to affect punny points. Yes, I said punny. So, I mean, it's Clark. We won't spend a ton of time with these, but I wanted to, like, show that this is what he looked like before we dive into a lot of text. The archives are your natural habitat. Oh, you're the archival Vashta Narada, yes? Okay, do we know who these people are? Is always the question. I don't, but apparently they're printed on a postcard. The only one I know is Clark, who is here. Oh, I know this. There's someone. Blah. This image is also elsewhere in the collection. They were a team working on a thing. I'll have to find it. Hi, Hannah. Do you love that I was like, they were a team working on a thing. This is the employees of the Naval Air Rocket, or Naval Air Rocket Test Station there in New Jersey in 1959. Some of looking at this reminded me of a TV show that was recent. Oops. trying to remember what it was. It was about a female scientist. But this lab here reminded me of a TV series, and I can't remember what it was. I think it was on Apple TV. But yeah, that would have been the kind of lab they were working in. If anybody does remember the name of the TV series, you can drop it in chat. See, are these the same people? The important question. I don't think they're all the same. It's possible, Shadows. This is Howard Strime, Eric Rao, and Thomas Maldonado with Clark. I'm guessing on some of those spellings because it's in cursive, and the only handwriting that I've seen of this person is these names, which means I don't have a lot to go on. There are other images with some of the people, but they aren't labeled. Well, if we find... Because I know there are other folders with images. So if we run across it, then maybe we'll find out what they were posing for. I think they were getting an award, but I can't remember what. Because I'm usually familiar with the images because I go through and look for pictures to use for the promotional images for the episode. Okay. I've got a couple of folders here that I had marked as interesting. And the first one that I'm going to do is this folder called Rocket Juice. Rocket Juice. Says JDC. Oh, John D. Clark. I know. I love the title of his talk here. Okay. Let me zoom in a little. So it's big on my screen because it's old typewriter in blue ink, which can be difficult to make out sometimes. Ladies and gentlemen, I have been asked to talk to you this evening on the subject of rocket propulsion chemistry, or the care and feeding of rockets. Now you see where I got the title. Now, the principles of this subject are of an immense and I have never seen this word before. Infinitile. It's not infantile. It's like the property of being infinite. Infinitile. I would not expect it to be spelled this way. And if anybody wants to check, is this an actual word that appears in the dictionary? I'm not sure it would be legal in Scrabble. Anyway. Now, the principles of this subject are of an immense and infinitile simplicity. But the application of the principles can lead to anything from ulcers to immediate admission to the receiving ward of a mental hospital. I should like to detail to you a few of the difficulties that are encountered in the business. First, I hope you will forgive me if I describe very briefly, for the benefit of those who came in late, what happens in a rocket. Gas is generated in a combustion chamber, heated to a very high temperature, at a pressure considerably above atmospheric, and then expanded through a nozzle. In this process, part of a thermal energy is converted to mechanical energy, and the momentum of the exhaust gas produces the forward thrust on the rocket. At present, the only practical way to heat this gas is by the chemical reaction which produces it, so we will defer the question of nuclear rockets to the next session. The performance, then, of this chemical reaction can be described by the equation I sub SP equals 294.98 times the square root of H over M and that lowercase n looking symbol. It's a lowercase Greek letter, and I don't really know the lowercase Greek letters at all. Hang on one second. Now I have to look. It's a lowercase eta. So the square root of H over M times eta. ETA. Which is certainly beyond my knowledge. But this talk appears to be targeted towards a more general audience. Thank goodness you played Kerbal Space Program. It's interesting because it does seem like it's targeted towards a more general audience. Which I like. Nope. I tried to find infinitile in the dictionary, and it defaulted to infantile. I think it's a made-up word, but technically authors are allowed. Yeah, I went to Webster's, and it doesn't recognize infinitile either. I wonder if infinitile, like spelled with an I instead of an A, I wonder if that would... Sorry, I'm digressing, but, you know, that's what this show is about, is learning things as we go. Ah! Interesting. So dictionary.com doesn't have infinitile, but it points to infinitive, which is the same thing, just with a different suffix. So it would be, again, the property of being infinite. Although in this case they're defining it in the language sense as the infinitive form of verbs and things like that. But the property of being infinite, infinitive, we already have a word that does that. But infinitile, I was able to make out what it meant, even though it wasn't actually a word. But yeah, writers make up words all the time. Shadows, you make up words all the time. I portmanteau all the time. So as long as the meaning is clear, that's all you need, right? Okay. Where was I? I was at the equation. Okay. I sub SP or specific impulse, has the dimensions of time and is defined as the thrust produced divided by the rate of consumption of the propellants, that is, pounds, say, divided by pounds per second. Multiplying I sub sp by the acceleration of gravity gives you the exhaust velocity. H is the heat of reaction involved in kilogram calories, and m is the mass of reactants in grams. 294.98 is a constant containing the conversion factor from thermal to mechanical energy, the acceleration of gravity, and so on. Eta is the thermal efficiency. I don't know if you're supposed to say it differently, like, because eta is the capital, so if it's a lowercase eta, I don't know if in mathematics it's referred to differently than a capital eta. If anybody here is super versed in mathematics and wants to specify, that would be interesting to learn, but I honestly have no idea, and I'm not sure where I would go to look that up. It might take me a bit, so it's not something I would look up on stream. The chemical reactions of interest in the rocket business, nearly all of them, obviously combustion reactions, give theoretical specific impulses in the range of 200 to 375 seconds. This is just to give an idea of the size of the thing I'm talking about. Now, obviously, since the job of a rocket is to produce a thrust, the specific impulse is the first thing we think about when we consider rocket propellants. Let us see what we can do to produce the highest possible impulse, taking the three factors H, M, and eta separately. First, we want a high H, and that means a combustion reaction. Right, because H is the heat. It is obvious, of course, that the reaction products must be gases, since a non-expansible solid or liquid isn't going to give you a lot of thrust. Although, I believe they eventually do... I believe solid rocket propellants are a thing now. Interesting that he's talking about gas because it's the development of liquid fuels that we're looking at, but I guess he's talking about the result of the reaction needs to be a gas. So it could start as solid or liquid as long as it's converting to gas in the reaction. Then we want a low M, which was mass, right? Yeah. And that makes sense. You want high combustibility, low mass, because the lower the mass, the more force you can get, the more effective force you can get from the combustion reaction. The more mass you have, the more work it would take to lift the rocket. Yeah, it has to go out the nozzle. Yeah. Okay, then we want a low M, which more or less confines us to the elements from hydrogen to fluorine. At times, chlorine appears a necessary evil in small amounts, and a few years ago, sulfur and... is it phosphorus? I don't know. Okay, come here, periodic table. I should just get a poster of the periodic table and put it up in my office, because I do have to refer to this often enough. And sometimes I'm just not sure. So Cl is indeed chlorine, S is sulfur, and I was correct, P is phosphorus. This was me guessing, because P I thought was phosphorus, but I was like, but is phosphorus pH? But no. I mean, it's been a long time since I actually took chemistry, but I loved chemistry. and I loved working with the periodic table and doing chemical reaction calculations using the periodic table. But like I said, it's been a long time. It's been more than 30 years since I did any of that. Okay, sorry. At times, chlorine appears. A necessary evil. I need to see if there's a video game that will let me do that. That would be interesting. Sorry. At times, chlorine appears, a necessary evil, in small amounts. And a few years ago, sulfur and phosphorus were considered in certain combinations, but have since been abandoned with the approval of just about everybody. Of the elements in the first row of the periodic chart, helium is out for obvious reasons. Interesting. He doesn't go into those reasons. I wonder what they are. I don't know what the combustibility of helium is. But ooh. Hello. Hi, Whimsies. Welcome in 16-bit Eric. Thank you so much for the raid. Welcome to Archival Adventures. I am Rogan27, aka Anthony Wright de Hernandez, Community Collections Archivist at Virginia Tech, and today we are exploring the care and feeding of rockets with the John D. Clark papers. Clark was a chemist and science fiction author and was involved with the Naval Air Rocket Test Station and later with some work at NASA, but was heavily involved in the development of the first liquid rocket fuels that were then used on the Apollo missions. So that's what we're looking at today. And right now we're looking at a talk of his called Rocket Juice, where I grabbed the title from for the stream. Because he starts out, I've been asked to talk to you this evening on the subject of rocket propulsion chemistry, or the care and feeding of rockets, which I just loved that, the care and feeding of rockets. We're not looking at his sci-fi stuff this week. That is planned, however, for a stream in the future. But yeah, welcome in, everybody. Hopefully everything was good on Eric's stream. I hope you had fun with Star Trek Online. If you're not already following Eric, I suggest you do so because the League of Whimsy is amazing and you'll have a good time. And if you're new here, I hope you stick around for a bit. Oh, Sayuri, thank you. Helium is non-reactive. So yeah, that would be why. Of the elements in the first row of the periodic chart, helium is out for obvious reasons. Lithium and beryllium have very few suitable liquid compounds, and we're talking about liquid-fueled rockets now, and boron compounds frequently give solid reaction products when burned, which, if we're trying for gaseous products, that's not what we're going for. And I'm on there in the shadows, of course. Yeah. Thank you for throwing those pun points, NeoGuts. Sorry. For most cases, then, we are confined to the elements hydrogen, carbon, nitrogen, oxygen, and fluorine. And chlorine when you can't avoid it. What's interesting... so this is talking specifically for liquid-propelled rockets. And I know, chemistry-wise, there is actual environmental benefit to burning sulfur at this point. Because burning sulfur actually puts into the atmosphere sulfuric acid compounds that help to negate the effects of global warming, but you have to put enough of it into the atmosphere. And burning sulfur around people, not great because sulfuric acid. The third factor is the thermal efficiency. It runs from about 35 to about 55%. Is it just me that thinks narts could be something Pinky from Pinky and the Brain would say? No, Shadows. When I first saw narts, that is sort of what I thought too. Which is part of why it's hard for me to remember that it is the... I've already forgotten. It's Naval Air Rocket Testing Station? It's a thing. And my brain is like... I know it, but yeah. I'm like, I know it, but I don't know it at the same time. Okay. Thermal efficiency. It's calculated by two general methods, both of which are based upon assumptions which are demonstrably false. The first, or frozen equilibrium method, assumes that the composition of the exhaust gas remains unchanged as it passes through the nozzle, and the second, or shifting equilibrium method, assumes that the gases remain at all times in thermodynamic equilibrium. Okay, composition remains unchanged, or in thermodynamic equilibrium. I think I understand. Also, I don't know the specific date for this paper. Sorry, I'm very distractible. It's circa 1955. But it's not specifically dated, so we don't know for certain. But I'm guessing it was it was co-located with other 1955 items. In other words, one method is based upon the assumption that all reaction rates involved are zero, the other upon the assumption that they are infinite. The true state of affairs is obviously somewhere between these two extremes, but exactly where, we don't know. Nor, if we did, is it likely that our mathematics would be capable of coping with the situation. Fortunately, the results of the two methods seldom vary by more than a few percent, and it is possible to make a reasonably reliable calculation of what will happen with a given set of propellants. The general equation for the efficiency is, in any case, given by the equation eta equals 1 minus P sub E over P sub C times R over C sub P, where P sub C and P sub E are the chamber and exhaust pressures, respectively. C sub P is the average molecular heat capacity of the exhaust gas, and R is the universal gas constant. It is in determining C sub P that the trouble comes in, since it obviously changes with the composition of the exhaust gases as well as with the temperature. Even to determine the exact composition of the gas at a given temperature, it is usually necessary to solve a dozen or so simultaneous equations. And although it can be done by brute strength and awkwardness, the only civilized way of handling the job is to turn it over to an electronic computer. He had a secondary career as a science fiction author, ostensibly successful, and I can tell why. He's a good writer. And these are not super straightforward. He's giving the technical detail, but he's also explaining it for the layman. Which is really hard to do, and this is well done. Assuming then the calculations have been made by some method or other, and we know what sort of efficiency to expect, how do we go about improving it? The most obvious way to do it is by increasing the expansion ratio, and there is a trend towards higher chamber pressures in the rocket business right now. The applicability of this method is, however, strictly limited, since higher pressures mean heavier chamber walls, more powerful pumps, and so on ad infinitum. ad infinitum, and you soon reach the point of diminishing returns. Because, yeah, as you add heavier walls, bigger pumps, etc., you're adding weight that has to be pushed by the propellant, and therefore the boost you get for being able to push more propellant is offset by the fact that you had to make it heavier to do it. Reducing the exhaust pressure is the only practicable way out, or the only practicable out in space. Helps. Electronic computer. Well, it's 1955, so electronic computer is a necessary distinction because a computer in 1955 was a person who did calculations, most typically a woman, and so if you watch the movie Hidden Figures, one of the 3 women that's featured in that movie was specifically a computer. And so computer at the time referred to people who did calculations. And a computer was somebody who was employed to do mathematical calculations. So an electronic computer is the machine. And over time, as electronic computers took over and people weren't being hired as computers anymore, the electronic got dropped because the only computer people were familiar with was the machine. I stumbled over that sentence and it was affecting the meaning. So where was I? Assuming then the calculations have been made by some method or other, and I was reducing the exhaust pressure is only practicable out in space, and even then, to expand the gases to 0 pressure would require an infinitely large nozzle, which might lead to manufacturing difficulties. I love the dry sense of humor. To expand the gases to 0 pressure would require an infinitely large nozzle, which might lead to manufacturing difficulties. Yeah, it might be a little difficult to make an infinitely large nozzle. The chamber pressures in use now range from about 250 to 750 psia, and most rockets are designed to exhaust to 14.7 psia. I know what psi is, pounds per square inch. What is the A? Oh, absolute. It's the absolute pressure, or absolute pounds per square inch. So it's mathematical, like talking absolute value instead of, which, okay, for the non-math people and for myself to refresh my memory, absolute value, or modulus of a real number x, denoted bars x, is the non-negative value without regard to its sign. So if it's number positive or number negative, the absolute value is number. So whether that pressure is negative or positive, we don't care. We just want the number. The other way to increase the efficiency, and that of more interest to chemists, is to decrease C sub P, which I've forgotten what C sub P stood for. The average molecular heat capacity of the exhaust gas. Hi, Bastion Cider. So the other way is to decrease. Wouldn't ASPE work better? I don't know, Shadows. The other way is to decrease the average molecular heat capacity of the exhaust gas. How do you do that? The lowest heat capacities are possessed by monatomic gases. By devising a reaction which will produce helium as its end product. But devising a reaction which will produce helium as its end product is out of the range of practical politics, so we have to be contented with reactions producing diatomic molecules such as helium fluorine? No, not helium. Hydrogen fluorine? Yeah, hydrogen fluorine. Nitrogen, hydrogen, and carbon oxide? Yeah. And so on. With C sub P's of 8 or 9 calories at the temperatures that interest us. In the order of 3,000 degrees Kelvin. Okay, now we have to talk about the Kelvin scale. What? Okay. I found a site. It's Celsius, but with inflation. Okay, this is the National Institute of Standards. Hello, brain. NIST, the National Institute of Standards and Technology. I completely forgot what the T stood for. Their Office of Weights and Measures. Okay, so Celsius temperature poem? Anyway, okay, so Kelvin's defined by taking the fixed numerical value of the Boltzmann constant, K, to be 1.380649 times 10 to the negative 23rd. Yeah, we're not going to go into all that. But... Oh, interesting. Celsius temperature poem. 30C is hot, 20C is nice, 10C is cold, 0C is ice. That's a cute little poem. Okay, but common temperature reference points. The surface of the sun in Celsius is 5,600. In Kelvin, it's 5,900. And in Fahrenheit, it's 10,100. The boiling point of water in Celsius is 100. In Kelvin, it's 373. And in Fahrenheit, it's 212. Body temperature in Celsius is 37. In Fahrenheit, it's 98.6. But in Kelvin, it's 310.2. The freezing point of water in Celsius is 0. In Fahrenheit, it's 32. And for some reason in Kelvin, it's 273. Kelvin is... Okay. Skipping the mathematical stuff because my brain won't process it. On the widely used Celsius temperature scale, water freezes at 0°C and boils at about 100. 1 Celsius degree is an interval of 1 Kelvin, and 0 degrees Celsius is 273.15 Kelvin. An interval of 1 Celsius degree corresponds to an interval of 1.8 Fahrenheit degrees on the Fahrenheit temperature scale. The standard temperature at the triple point of water is provided by a special cell, an evacuated glass cylinder containing pure water. When the cell is cooled enough so that a mantle of ice forms around the re-entrant well, the temperature at the interface of solid, liquid, and vapor is 273.16 Kelvin. Thermometers to be calibrated are placed in the re-entrant well. Take the numerical value of the Boltzmann constant, where the kilogram, meter, and second are defined. 0K is commonly referred to as absolute zero, when all chemical reactions would cease. Yeah, it uses the scale of Celsius, but puts 0 at absolute zero. So it's useful for calculation. Because Celsius puts 0 at the freezing point. Kelvin puts it at absolute zero, which is basically the place where chemical reactions would cease. Like, everything stops. If my brain is recalling things correctly, which doesn't always happen, but that's what the internet is for. The lowest theoretically possible temperature. A state at which a system's internal energy and in ideal cases entropy reach their minimum values. Because twice the Kelvin is twice the energy. Okay. I love, like, these are things that I'm familiar with, but have never delved into the specifics, which is part of why I love doing this, because I get to learn things. Okay. In the order of 3,000 degrees Kelvin, or about half the temperature of the surface of the sun. And we are usually forced to accept things like H2O and CO2, water and carbon dioxide, with heat capacities of 13 to 15 calories, while the misguided engineer who attempts to burn carbon with fluorine will have to contend with CF4, which would be... How would you say that? Oh, carbon tetrafluoride. It's been 30 years. Which is a perfluorocarbon. Yay! A potent greenhouse gas. Such as contend with carbon tetrafluoride with a heat capacity of about 30. So this is what we try to get. A diatomic exhaust gas with a very low molecular weight and an extremely high heat of formation. The only thing that would fill the bill completely is hydrogen produced from atomic hydrogen. So if any of you know how to make and to store large quantities of atomic hydrogen, just let me know. The specific impulse would be about 1,000 seconds, about 5 times that of the V2, which was one of the German rockets developed in World War II. And I think that I could guarantee you not only a permanent job, but a couple of medals and maybe a Nobel Prize or two. I do love his dry humor. Okay, we are about to be attacked by an advertac. So I'm going to go to the Be Right Back screen, and we will return after the mandatory advertisements pushed on us by Twitch are done. See you soon. Thank you, Shadows. I'm not sure why it's doing that. I will have to fix that. It did that last week, too, and That is a new thing it's doing. I'm making a note so that I can fix it. I know there were a bunch of updates that happened last week, and so something in the software apparently has changed something, and I need to find it. Anyway, the ads should be done. We should be ready to keep learning about the care and feeding of rockets. Now that we have some now that we have... Wait, no. I'm too far ahead. Okay. Failing atomic hydrogen, we have to compromise. The usual compromise is to run the rocket somewhat on the fuel-rich side. That is, with not quite enough oxygen to burn all of the carbon and hydrogen to carbon dioxide and water, so that there will be some hydrogen and some carbon oxide in the exhaust gas. The improvement in the quality of the exhaust gas more than makes up for the loss in energy. So that maximum performance is usually found from 10 to 50% of the fuel-rich side. Nitrogen is frequently present, for although it contributes no energy, it helps the quality of the exhaust gas. Now that we have some idea of what we want to come out of the tail end of the rocket, what do we put in the front end to get that result? Liquid propellants can be divided into fuels, oxidizers, and monopropellants. Fuels are just what the name implies, something that will burn. Usually that means hydrogen or compounds of hydrogen with nitrogen, or organic compounds containing hydrogen and carbon. Fuels do not generally vary much in performance with a given oxidizer. Alcohol is a good fuel, kerosene or jet fuel is good, and it will take a pretty good motor to tell the difference in performance if they are burned with the same oxidizer. It is always useful, of course, if you pick a fuel with an endothermic heat of formation so that when it breaks up, you get a little energy dividend, and don't have to spend some of the energy from the formation of the exhaust gases in breaking up the propellant. Hydrazine and uns dimethylhydrazine? What is UNS? Unsymmetrical dimethylhydrazine. At room temperature, unsymmetrical dimethylhydrazine is a colorless liquid with a sharp, fishy, ammonia-like smell typical of organic amines. Samples turn yellowish on exposure to air and absorb oxygen and carbon dioxide. It can be mixed with water, ethanol, and kerosene at concentrations between 2.5% and 95% in air. Its vapors are flammable. It's not sensitive to shock. Interesting. Okay. Hydrazine and unsymmetrical dimethylhydrazine are examples of such fuels. Fuels aren't generally, as I said, much of a problem. Anybody can come up with a new one, and it will probably be not much better and not much worse than the ones we are using now. Oxidizers, which are needed to burn the fuels, are another and a real problem. I don't believe that there are more than 3 or 4 oxidizers in actual operational use today, and none of them make us very happy. All oxidizers can be divided into 3 groups. First, there are the pure oxidizers: liquid oxygen, liquid fluorine, liquid fluorine dioxide? No. That would be oxodifluorine or something like that. Oxygen difluoride. Hi, Be Right UK. Thank you so much for the 61-month resubscription. Let's just hope they're not trying to use dihydrogen monoxide as a fuel. I mean, dihydrogen monoxide is more likely to be the resultant leftovers of the burning of the fuel, given what was being said earlier in the paper. Where was it? Okay. Oxygen difluoride. So there are pure oxidizers, liquid oxygen, liquid fluorine, liquid oxygen difluorine, etc. They generally give the highest performances. The second group comprise compounds of oxidizing elements with a carrier element. Nitrogen dioxide, nitrogen trifluoride, chlorine trifluoride. Yeah, trifluoride. It's been 30 years since I read chemical formulas consistently, so which give the next highest performance. And third, there are the byproduct. Yes, thank you. You were just trying to take the water. I read that as just trying to take the piss, but and third, there are the workhorse oxidizers, which are unfortunately already partly reduced. Nitrogen trifluoride is scary poisonous. Nitrogen trifluoride is the inorganic compound with the formula NF3. It is a colorless, non-flammable, toxic gas with a slightly musty odor. In contrast with ammonia, it is non-basic. It finds increasing use within the manufacturing of flat panel displays, photovoltaics, LEDs, and other microelectronics. NF3 is a greenhouse gas with a global warming potential 17,200 times greater than that of carbon dioxide when compared over a 100-year period. So it is toxic. Skin contact with nitrogen trifluoride is not hazardous, and it is a relatively minor irritant to mucous membranes and eyes. It is a pulmonary irritant with a toxicity considerably lower than nitrogen oxides, and overexposure via inhalation causes the conversion of hemoglobin in blood to methemoglobin, which can lead to the condition methemoglobinemia. That is hard to say. Methemoglobinemia, which is a condition of elevated methemoglobin in the blood. Symptoms include headache, dizziness, shortness of breath, nausea, poor muscle coordination, and blue-colored skin. Cyanosis. Methemoglobin is a hemoglobin in the form of a metalloprotein, in which the iron in the heme group is in the iron 3 plus ferric state, not the iron 2 plus ferrous of normal hemoglobin. Wow, interesting. I don't understand all of it, but it is fascinating, and if I had a bunch more time, I would follow that rabbit hole. But I want to finish this document so we can see some more. Workhorse oxidizers. Already partly reduced. Nitric acid is one of them, and concentrated hydrogen peroxide is another, both already carrying hydrogens with them. Of all the oxidizers proposed, the only ones I believe in actual use in operational missiles today are liquid oxygen, nitric acid, and hydrogen peroxide. Oxidizers are the big and potentially promising field for propellant research. Producing a new oxidizer is not easy, but here is the spot where work has to be done, and the rewards could be great. A fuel and its oxidizer must always be considered together, since both contribute to the exhaust gas. For instance, it would be highly inadvisable to burn a hydrocarbon with fluorine. Hydrogen fluorine would appear in the exhaust gas, which is fine, but there would also appear, depending on the mixture ratio, free carbon or carbon fluorides. The carbon will contribute little to your performance, and the carbon fluorides not much more. The first will be a solid, and the second will have too high a heat capacity. It would be better either to use ammonia as a fuel, in which case your gases would be hydrogen fluoride, nitrogen, and hydrogen, the first contributing a great deal of energy and the other two with excellent heat capacities, or to burn your hydrocarbon with oxygen difluoride. Then you would get hydrogen fluoride and carbon oxide, high energy, excellent gas characteristics, and a gratifying performance. The starting properties of a fuel oxidizer combination must be considered with some care. If alcohol is burned with oxygen, you have to start the fire with a squib or some similar device. If you're unfamiliar, a squib is basically a really small explosive. Squibs are used in, or were used, I don't know if they still are today, probably, but squibs, a common usage that people would be familiar with is like in television production or stage production. If you need it to look like somebody's been shot and you need blood to spontaneously appear where a bullet wound is, you've got a squib, and the squib will go off and explode a little packet of dyed material to make it appear like there's blood. On the other hand, if red fuming nitric acid and aniline are used, the combination is hypergolic, which is self-igniting, or that is self-igniting. This can be a useful property, considerably simplifying the plumbing, but the mere fact that a combination is hypergolic doesn't guarantee a smooth start. If the ignition is a bit delayed, say 1 or 2/10 of a second, trouble can be confidently expected. The fuel and oxidizer will spray into the chamber, collect there in a puddle, and then ignite all at once. The results can be spectacular and noisy, and can produce an astounding amount of flying hardware. The engineer in charge then receives the order of the pretzel thrust mount, and thanks the Lord that control room walls are made of 3 feet of concrete. It has happened to all of us. I do love his humor. There are likely to be similar difficulties with the third type of propellant, the monopropellant, in which the fuel and oxidizer are combined in a single fluid, either as a single chemical compound or as mechanical mixtures or solutions. Nitromethane is an example. Mechanically, the monopropellant is an excellent idea, simplifying the design, requiring only one set of fuel tanks and pumps, needing only a simple injector, and with many other obvious advantages. Unfortunately, high-energy monopropellant is generally only a polite name for liquid explosive. And if for some reason the propellant explodes in the chamber, there is a high probability that the explosion will move right up the fuel line into the tank, and the results will be deplorable. If a motor is designed to run for more than a few seconds, the chamber walls must be cooled, since combustion temperatures are above the melting point of almost all structural materials. The usual way of doing this is to pass the fuel or the oxidizer over the outside of the chamber before injection. This so-called regenerative cooling has a good many advantages. Not only are the chamber walls kept below their melting point, but the heat loss through them is salvaged by the propellant and brought back into the chamber where it will do some good. With a properly designed motor, true adiabatic conditions are approached. Adiabatic? Sorry. I love new words. It's part of the learning we get. Adiabatic, adjective, relating to or denoting a process or condition in which heat does not enter or leave the system concerned. Okay. I was familiar with adiabatic, but not adiabatic. Also known for the phrase, like a damp squib. Well, a damp squib isn't likely to go off. Okay. I got lost. Adiabatic. Okay. With a properly designed motor, true adiabatic conditions are approached, and the efficiency approaches the theoretical maximum. But the heat capacity of the fuel must be considered, as well as its thermal conductivity and its stability under the temperatures attained. If it decomposes appreciably under these conditions, either the cooling passages will be clogged up with the decomposition products, or the whole motor will explode. Under any circumstances, the stability of the propellant cannot be ignored. A high-energy propellant, almost by definition, has a tendency to decompose. If that tendency is encouraged by mechanical shock, by not too immoderate temperature conditions, by catalysis of some sort, or, as is generally the case, by causes unknown, the results can be disconcerting. Liquid acetylene has a lot of energy in it, but nobody in his right mind would care to use it as a rocket propellant. And while nitroglycerin has been suggested as a monopropellant, there has been a noticeable reluctance on the part of the engineers concerned to do much about it. An extreme... Sorry. I really like his humor. Gee, I wonder why. Nitroglycerin, if you don't know, old dynamite will sweat nitroglycerin, and nitroglycerin is very unstable. If you shift old dynamite that is sweating nitroglycerin, the slight vibration can cause it to explode. If you pick up old dynamite that's sweating nitroglycerin, I don't know why you would, moving it and having some drops of nitroglycerin fly off and hit something will explode. It goes boom at anything. Oh, the Vinny from the Atlantis movie. I don't know the specific quote, but I know the character. So, while nitroglycerin has been suggested as a monopropellant, there has been a noticeable reluctance on the part of the engineers concerned to do much about it. An extremely important consideration is the density of the propellant. Liquid hydrogen is energetically one of the best possible chemical fuels, but its density is approximately 1/14 that of water, and any reasonable amount of it will take an unconscionable amount of tank space. That means more dead weight and trouble in general. And if you are designing a small missile to operate in the atmosphere, it will mean more air resistance and a lower performance of the missile itself. If the problem were to design a rocket to take off from the moon with no air resistance to consider, this factor obviously would lose much of its importance. On the other hand, nitric acid is a frequently used oxidizer, as much because of its high density, 1.5, as because of the large oxygen content of the molecule. While with a density like that, you can get a lot of oxygen in a very small tank. Other physical properties must be considered. it can be assumed by definition that the propellants of a liquid-fueled rocket must remain liquid over the operating range of temperatures and pressures. And it must be remembered that a rocket does not run in a thermostat. The outside temperature, and hence that of the propellants, may vary from 80 degrees below 0 centigrade to 60 above. If the propellant freezes solid or becomes too viscous for the pumps to handle, when the rocket is at 50,000 feet, the flight is likely to come to a premature halt. And if it boils off as the missile is taking off from the surface of the Mojave Desert, the feed rate is going to vary in a highly unpredictable manner. That's not good. That's nitroglycerin. Don't move. Don't breathe. Don't do anything except pray, maybe? Then Mole shouts, boom. Yes. It's been a while since I watched it, but I remember that. Occasionally, pressurizing the fuel tanks is an acceptable answer. Ammonia, to mention one fuel, and chlorine trifluoride, to mention an oxidizer, can be liquefied at room temperature by the application of quite moderate pressures. But in this case, and sometimes with propellants that are normally liquid, the vapor pressure of the material can cause trouble by inducing cavitation in the fuel pumps, vapor locks in the lines, and so on. It is possible, of course, to use substances like liquid oxygen and to accept the inevitable handling difficulties and evaporation losses, but its use involves so many questions of refrigeration, insulation, and so on that it is unlikely to be used extensively in small missiles where heat transfer is likely to be high. Liquid hydrogen, with much to recommend it, is an extreme example of the difficulty of working with liquid permanent gases. Its boiling point is not only extremely low, second only to that of helium, but at low temperatures the molecule changes from the ortho to the para state, evolving heat and accelerating the evaporation. Even methane, carbon tetrahydrogen, which would make an excellent fuel, would have to be handled like liquid hydrogen or oxygen. Which would have to be handled like liquid hydrogen or oxygen, since no conceivable pressure can liquefy it at room temperatures. And merely compressed gases are out of the question. They require heavy tanks, which means more weight, and the density of even the most highly compressed gas is too low to permit an adequate amount of fuel in a tank of reasonable dimensions. There is another consideration that presents itself. The propellant must be stored, perhaps for a long time, in some sort of a container, and it must be kept in the tanks of the rocket. Some of the best oxidizers, such as red fuming nitric acid, approach the universal solvent in activity, and are more likely than not to attack the storage drums, eat holes in the fuel tank, and to abolish the pump unless the material for these objects is chosen with more than ordinary care. Even if the corrosion is not mechanically serious, the propellant may be seriously contaminated by the material of its container. Other propellants, such as hydrogen peroxide, tend to decompose, and the decomposition may quite easily be catalyzed by some metal which we would like to use for the fuel tanks. Occasionally, peroxide will start to decompose on its own, for no apparent reason. The decomposition liberates heat, which accelerates the decomposition, which liberates more heat, and so on, frequently ending in a first-class explosion. Under any circumstances, the material must be vented at all times to avoid the chance of a pressure buildup. Liquid oxygen, too, must be vented, and is extremely difficult to store for any length of time. Apollo 13, that disaster happened partly because of liquid oxygen. In general, however, the storage problem can usually be solved in a more or less satisfactory manner, and it is not usually entire beyond the wit of man to choose structural materials that can contain the propellants, but the answer in any given case is not always entirely obvious. The propellant must be handled. Somebody has to transfer it from the storage container to the tanks of the rocket, and he frequently has a phenomenally unpleasant job on his hands. Red or white fuming nitric acid can start a fire if they splash on anything combustible. The fumes, nitrous oxide, given off by the red acid, are about as dangerous as phosgene. What is phosgene? Phosgene is an organic chemical compound with the formula COCl2. It is a toxic colorless gas in low concentrations. Its musty odor resembles that of freshly cut hay or grass. It can be thought of chemically as the double acyl chloride analog of carbonic acid, or structurally as formaldehyde with the hydrogen atoms replaced by chlorine atoms. Oh, that sounds pleasant. Extremely poisonous. Was used as a chemical weapon during World War I, where it was responsible for 85,000 deaths. Highly potent pulmonary irritant and quickly filled enemy trenches due to it being a heavy gas. Well, we don't want phosgene, that's for sure. About as dangerous as phosgene. If either acid touches the skin, it will produce a very nasty burn. It also corrodes almost anything that it touches. Concentrated hydrogen peroxide isn't particularly corrosive, and its fumes are merely oxygen and water. But it will ignite with many combustibles, including wool. Did you know that? I didn't know that. Hydrogen peroxide will ignite with wool? More than one operator has been killed when a big splash of the material on his clothes converted him into a flaming torch. Aniline is extremely poisonous and is absorbed through the skin. A big splash of it, if not removed immediately, can lead to cyanosis and death. Liquid oxygen by itself is relatively innocuous, although it can freeze a hand quite solid quickly enough, but some of it combined with an inflammable substance and a spark can produce an explosion that is a long way from innocuous. And all of the fuels, as opposed to the oxidizers, are naturally quite flammable, generally about as much so as gasoline. This is why you peel your sheep. Probably the most vicious propellant that has been proposed is liquid fluorine. It evaporates off like oxygen. The vapor is highly toxic. The liquid or the gas will produce an extremely dangerous, painful, and slow-healing burn on the skin, which incidentally produces systemic poisoning at the same time, and it ignites spontaneously with almost everything, including wood and all combustibles, as well as such things as sand and asbestos and such alleged firefighting agents as water, carbon tetrachloride, and carbon dioxide. You gotta love something that ignites with water. Like phosphorus. In short, almost everything that we work with in the rocket business is flammable, explosive, toxic, corrosive, or smells horribly, or has some combination of these characteristics. And not long ago, one industrial outfit tried to sell me a propellant that also drew flies. If the designer can find a propellant pair that can be loaded and sealed into the missile at the factory, he can consider himself extremely lucky. Otherwise, the loading will generally be a difficult and hazardous field job, involving unremitting caution, cumbersome protective clothing that usually causes more accidents than it prevents, and with the ever-present danger of a really serious accident. Then we have the considerations covered by that much-abused word, logistics. Assuming that we have found a really good propellant, can we get it when we want it, and as much of it as we want? The case of aniline, now considered to be obsolescent, is pertinent. Aniline is a fairly good workhorse fuel. It ignites well, has a good density, a fair impulse, good storage characteristics, and not too difficult handling characteristics. But it's made from benzene. And in the course of a dress shirt war, there's never enough benzene available for half the things we would like to make from it. So we can't rely on aniline if we want to make 1,000,000 missiles. And the final consideration is the vulgar one known as money. If we are building a rocket to go to the moon, or one designed to deliver a hydrogen warhead to the center court of the Kremlin, price may be no object. But if we want to build 700,000 missiles to knock off bomber formations, the price is something that cannot be entirely ignored. Briefly, there is no all-purpose propellant combination. The problems involved in a satellite are quite different from those involved in anti-aircraft missiles. In the former case, the performance is all important. In the latter, ease of manufacture, storage, and handling may well be so important as to make a slight loss of performance perfectly acceptable. But even if the ideal propellant does not exist, its characteristics have been described to us chemists by the engineers, with the demand that it be produced by day after tomorrow. It is a monopropellant with the following properties. 1. It must have the performance of hydrogen and fluorine combined with the density of osmium, the coefficient of expansion of fused quartz, and the freezing point of helium. The vapor pressure and boiling point of tungsten would be acceptable, as would the viscosity and thermal conductivity of helium-2. The specific heat must equal that of liquid hydrogen, while the thermal sensitivity must not exceed that of graphite, nor the shock sensitivity be greater than that of Krupp process armor plate. 3. The chemical stability and corrosivity of argon are mandatory, and the propellant must be packageable and indefinitely storageable in paper bags. The availability must be equal to that of air, but only, of course, within the continental limits of the United States. 4. The odor should resemble that of Chanel No. 5, the toxicity should be that of Canadian Club, and the price that of dirt. Bids from the chemical industry are invited. That was good and well worth the time it took to read the whole thing. Despite the fact that it's the only document we've actually looked at today. We've got a few minutes to look at some more. I know, it's been really delightful, and honestly, we can do as many streams with this collection as we want. Like, my plan was to do some science-y and then some sci-fi. We might do a second science one, just because he's a really good author, and these are really interesting. Okay, so this one is Dark Horse in the Propellant Race. Because science! Yeah, I do love it. John D. Clark, a physical chemist by trade, was born in Fairbanks, Alaska, received his BS at Caltech, his MS at Wisconsin, and in 1934 his PhD at Stanford. After working for such concerns as General Electric, John Waith and Brothers, and Wallace and Tiernan, he came to the U.S. Naval Air Rocket Test Station, then just starting as the Naval Air Rocketry Lab, or Air Rocket Laboratory, in November 1949. He has been in the rocket business there ever since, founding the chemistry branch of the station in 1950 and becoming head of the propellants division in January 1956. The major part of his efforts for the past 4 years has been directed towards the development of usable high-energy monopropellants. He is a member of the ARS and has been elected a member of the Monopropellant Test Methods Committee. His extracurricular activities include driving a sports car, raising Alaskan Malamute dogs, studying cosmology and the history of naval architecture, and trying to invent a dryer martini. Monopropellants. The Third Generation? By John D. Clark. Monopropellants have long been stepchildren, the Cinderellas of the propellant family. For years, the biopropellant liquid systems held the center of the stage, and now the solids, particularly those found more easily in a salesman's notebook than in a rocket, are elbowing their way into the spotlight, loudly proclaiming their ability to do everything that the liquids can do, only better. In the meantime, the liquid monopropellant has been pointedly ignored. In the minds of most rocket engineers, and in actual fact, until quite recently, there were just two sorts of monopropellants. The first were low-energy compounds like ethylene oxide, all right for running an APU. APU is an alternate power unit typically found on airplanes to run necessary flight control systems if all of the engines go out. Like, if the electrical source from the engines stops, the APU can be deployed to provide power so that the instruments can be read and potentially used. All right for running an APU, but certainly without the performance needed for primary propulsion. The other group, with energy comparable to some of the bipropellant systems, consisted solely of touchy and violently explosive liquids with a strong family resemblance to nitroglycerin. Definitely nothing to use in a rocket. Well, the engineers were right. The candidates for the title of high-energy monopropellants came in two families. The first consisted of pure chemical compounds, such as methyl nitrate, CH3NO3, a molecule with a reducing end and oxidizing end, separated by a pair of firmly crossed fingers. Apparently they explode when you mix them, and so you prep it and hope that they don't mix prematurely. Hence the firmly crossed fingers. The second family consisted of solutions of a fuel in an oxidizer, as benzene and nitrogen tetroxide, and would have been very useful as high explosives if there had been any method of handling them without getting yourself blown up. High energy monopropellants, with very good reason, were a byword and a hissing. This reason, gentlemen, no longer exists. A certain family of monopropellants of the mixture type under development at the Naval Air Rocket Test Station for the last 4 years possess such a combination of favorable properties that they may well take the place of both bipropellants and solids in many applications, and appear likely to power many of the third generation of missiles. These propellants are not a dream. They have been made, handled with perfect safety, and fired not once, but scores of times. Their nature and composition must unfortunately remain classified since, once the general idea is known, the synthesis of the propellants and the possibilities of the systems are as obvious as a ham sandwich. Since the curse of previous high-energy propellants was the dangers attending to their use, the safety angle should be considered first. The new propellants are apparently completely immune to ordinary mechanical shock. A bottle of the material has been dropped 30 feet onto concrete, and all that happened was that the bottle smashed. They appear to be completely immune to adiabatic compression, unlike such propellants as N-propyl nitrate. They can be exploded by gunfire or by a sufficiently violent explosive shock, as can solid propellants, or indeed almost any other intimate near okay. Indeed, almost any other intimate near stoichiometric mixture of an oxidizer and a fuel. But no conceivable maltreatment in shipping or handling seems to bother them. Stoichiometric? Really? Relating to or denoting quantities of reactants in simple integral ratios as prescribed by an equation or formula. Clear as mud. Stoichiometry, the relationship between the relative quantities of substances taking part in a reaction or forming a compound, typically a ratio of whole integers. Okay. Anyway, no conceivable maltreatment in shipping or handling seems to bother them. From this point of view, they are no harder to live with than are double-base solids. They are safe in storage at any temperature that will be encountered, and they are not subject to catalytic decomposition. They are not a fire hazard. They will not even burn at atmospheric pressure. And what fumes they give off are much less troublesome than those of, say, RFNA. Okay, what's RFNA? Does anybody know? Red fuming nitric acid. Since the primary business of a propellant is to propel, their performance is the next thing to consider. This family of propellants has theoretical specific impulses in the 225 to 230 SEC region, shifting equilibrium 300 over 14.7 psia, and achieve 94 to 95% of this experimentally with an L of 50 inches and an extremely simple injector. No idea what that means, but I don't have enough time to look it up. Ribonucleic acid. I like that, but it's red fuming nitric acid. One very successful injector consisted of 6 commercial oil burner spray nozzles at 79 cents each. This performance, combined with a density of 1.3, makes them competitive not only with the solids, but with the workhorse bipropellants. They can be used for regenerative cooling. Their freezing and boiling points are no problem. They boil near 200 degrees Fahrenheit, and most of them freeze below minus 100 Fahrenheit. Nor is there any difficulty in long-term storage in stainless steel or aluminium. Corrosion and pressure buildup are negligible, and pre-packaging is easy. From the Greek meaning element and measure, stoichiometric. Logistically, they are very attractive. See, I'm sight reading these documents, and when I come across a word like near stoichiometric, it takes me a minute to figure out how to say it. Logistically, they are very attractive. The raw materials are cheap and abundant, and they can be synthesized with existing and standard equipment by any chemical process plant above the level of a garage hobby shop. Now, consider a system using such a monopropellant in comparison first with a solid and then with a bipropellant system. 1. They have an appreciably higher ISP than a solid at comparable chamber pressures, since their oxygen balance can be adjusted for maximum performance. 2, since regenerative cooling is possible, the burning time can be made as long as is desired. 3, throttling, cutoff, and thrust programming are easily accomplished. The optimum acceleration for each stage of the flight program can be chosen. 4, vehicle control is possible with a gimbaled thrust chamber. 5, CG control of the missile is easily accomplished without the use of an awkward blast tube likely to burn out and sure to reduce performance. 6, the propellant is indifferent to storage and handling conditions. It will not crack when too cold or in transit or when dropped, and the burning rate does not vary appreciably with propellant temperature. It is always completely homogeneous, unlike a composite solid, in which absolutely uniform distribution of the oxidizer through the fuel matrix is not always achieved. The propellant is 8. The propellant is likely to be cheaper than a solid, and if the missile is too large for pre-packaging, the propellant can be easily shipped separately. In contact with the usual bipropellant system, the monopropellant system, 1, needs much less plumbing. I think it's supposed to be contrast, not contact, but needs much less plumbing, roughly half as much, and needs only 1 propellant tank. 2, can easily be prepackaged and will keep indefinitely without corrosion or stability problems when so prepackaged. 3, needs no mixture control apparatus. The oxygen balance, once chosen, is built into the propellant and cannot vary under any circumstances. The corollary to this is that there can never be any outage or unintentionally unconsumed propellant. 4, needs a much simpler and cheaper injector, since mixing problems do not exist. Much combustion instability has been traced to incomplete mixing of fuel and oxidizer. 5, all of the propellant can be used for regenerative cooling. 6, greatly improved reliability is achieved due to the reduction in the number of components. These are some of the general advantages of such propellants, those independent of the missile design and size. A small missile, say ground to air using one of the new monopropellants, could be designed to be as ready to go as a solid. Its power plant would not require a single solenoid valve, and it could be fired simply by closing one switch. No propellant servicing and replacement would be needed. The tank would be loaded at the factory and ignored from then on. If a large missile, say an IRBM, were in question, the use of such propellants would avoid the problems involved in casting and shipping a large grain, if solids were the competition, and if liquids were being considered, the countdown could be drastically reduced as far as the propulsion system is concerned. There wouldn't be any more need to worry about oxygen valves and/or boil-off. In this respect, it has been calculated that in such a missile, a monopropellant with an I sub SP of 215 seconds is competitive with a bipropellant producing 250. All because of the simplification of the hardware and the elimination of the outage. The possibilities from the designer's point of view are rather obvious. Monopropellants, now in an advanced stage of development, will make it possible to design a missile which combines the readiness and nearly the simplicity of a solid-propelled rocket with the flexibility and performance of a bipropellant job. The solids and the bipropellants are racing neck and neck, but they might be well advised to look over their shoulders. There's a third horse in this race, and he's coming up fast. This is apparently his response to, accompanied by this letter, 26 May 1958. Dear Mr. Neubauer, in answer to your letter of 19 May, I would be happy to write an article on monopropellant for astronautics. It will, of course, need security clearance, which may pose some difficulty since the most interesting things in the field are classified. The title I have in mind would be Monopropellants, the Third Generation, which would start a fight, if nothing else. If you will tell me how long an article you want, I'll try to get things rolling. I do love his sense of humor. I'm really curious after reading that as to what those monopropellants ended up being, because this article makes it sound like they achieved all of the things that he was implying were not easily achievable in the previous thing we read. There's more in that folder, and I will plan to continue with Dark Horse in the propellant race next time we come back to the John Clark papers, which I currently have scheduled for March 4th, 1 month from today. Honestly, that was way more fun than I expected it to be, and also still educational. I learned a bunch. I hope you did. I'm excited to explore more of this collection, honestly. So hopefully you'll return in the future for more from the John Clark papers. I don't know what I'll call the next one. It's probably just going to be the Care and Feeding of Rockets Part 2, because we haven't fully explored that yet. But fingers crossed that the credits actually function. Apparently not. They didn't work last week either. I don't know what happened. Well, I will have to work on that for next week. I thought I had fixed it, but I need to do more testing. I have been your host, Rogan27, aka Anthony Wright de Hernandez. Thank you to my moderators, Hannah and Lord Portico. Thank you, 16-Bit Eric, for the raid. Thank you, Be Right UK, for the resubscription. Thank you to... was it Neogats? Somebody had a streak. Oh, Shadows of Life. Thank you for the streak. And of course, thank you everybody who hung around for any period of time and learned along with me. It is time now, though, to figure out where we're going to raid as we continue forward. So Stephen is on, as always. The aquarium is live. Paleontologizing. I'm still gonna go to Stephen for today. Stephen was here, observing. Stephen has a wonderful community, and it's always worth raiding. So, we'll pop on over to Stephen Joy's for some lovely game times. Stephen has a wonderful community. I highly encourage you to join. And ask for a tiny hat. There are many options. But yeah, thank you everybody for joining me. Hopefully I will see all of you again soon. Next week, I have the Jesse Wilcox Smith advertising illustrations. You'll probably recognize them, even though they're from the late 1800s to the early 1900s. So we'll be looking at those next week, and then after that I've got probably heraldry and insignia. We got stuff coming up. Thanks for being here. Hope I see you soon. Until then, get out there and do some shenanigans, but also keep exploring history.